Welcome to Texas State University's Chemistry 2330, Introduction to Organic Chemistry. I'm your guide, Dr. David Irvin, and we will continue with Chapter 7, Part 4, Haloalkanes. In addition to doing nucleophilic substitution reactions with alkyl halides, we can also do what we call beta elimination. What that means is we remove the halide from the alpha carbon, but we also remove a hydrogen from the carbon next to it, or the beta hydrogen. The net result here is we're removing a hydrogen and a halogen, so we actually are eliminating an acid. And we typically use this in the presence of a base, or a strong or weak base. Okay, so basically what we're going to end up doing is to create, we're going to break a sigma bond. We're going to break two sigma bonds and form a pi bond from those electrons. Okay, so whenever we do this, the major product of a beta elimination is always going to be the more substituted alkene. Just like when we try to form the more substituted carbocation, we want to form the more substituted alkene. So if we have a possibility of making something cis or trans, or have three functional groups on it, it's going to try to get three or four groups hanging off the double bond, if at all possible. So let's look at that in a little bit more detail here. In the case of this 2-bromo 2-methylbutane, what we can do is we can actually remove a hydrogen from one of these methylenes, a hydrogen from this methylene, or a hydrogen from this methylene. Because when we remove the hydrogen from this methylene, we end up with three substituents on our alkene. It is the major product. Notice if we remove either one of these other hydrogens, we're only going to have two substituents on this alkene and two hydrogens. Therefore, it's the minor product. In the case of this cycloalkane here, the 1-bromo 1-methyl cyclopentane, we can remove a hydrogen from this methyl group here, or we can remove the hydrogen from the group next to it. If we remove it from here, we only get a di-substituted alkene. In the case of removing this proton here, we'll end up with a tri-substituted alkene. That means the tri-substituted alkene will be the major product, and the di-substituted will be a minor product. So Zaitsev rule says you'll always get the more highly substituted double bond. Okay. There are two limiting mechanisms in beta elimination, just like there are in the nucleophilic substitution reactions. There's an E1 mechanism where we actually break the carbon halide bond first, forming a carbocation. And then there's the E2 mechanism. That's where we're pulling the hydrogen off. As the electrons are coming in from that, the halogen leaves at the same time. In the case of E1, the rate determining step only involves the concentration of the alkyl halide. In the E2 step, it involves the concentration of the base and the alkyl halide, that are just like in an SN2 reaction or an SN1 reaction. Okay, so in an E1 reaction, the first thing we're going to do is we're going to break the bond to give a stable molecular ion. And in that case, we're actually going to remove the electrons from the sigma bond. They leave with the bromine, generating that carbocation. Remember, that carbocation is trigonal planar. The next thing we're going to do is we're going to remove a proton with a base, a Lewis base of some sort. When the Lewis base comes in, the electrons from the Lewis base are going to form the new bond with hydrogen, leaving the two electrons that were in that former sigma bond to generate the double bond. Now, when that deprotonated species goes away, we are left with our neutral alkene. Okay. In the case of an E2 reaction, this happens all at the same time, meaning the base will come in and electrons will start forming a new bond with our hydrogen here. The electrons that were the sigma bond between the hydrogen and the carbon now kick in to form our new pi bond When it does this, these electrons right here are then kicked out with the bromine, and the bromine leaves as an ion, and our base typically ends up as a neutral species. So in this mechanism, we end up with our alkene and our protonated Lewis base. Okay, so just like in alkyl halide substitution reactions, E1 and E2 reactions have favorites. Okay, primary alkyl halides do not occur by E1 reaction. The reason is, in an E1 reaction, you have to form a carbocation, and therefore primary carbocation is not stable. Therefore, an E2 reaction is favored. When we have a secondary alkyl halide, remember it forms a moderately stable carbocation, which means it can go E1 or E2 based on the strength of the base. So for weak bases like water and alcohols, they are neutral Lewis bases. These can undergo E1 reactions. They're going to wait around for the carbocation to form before deprotonating the substrate. In the case of strong bases like hydroxide or the alkoxide, the salt of an alcohol, because we now have strong bases, we can now do the E2 reaction. We don't have to wait for the carbocation. In the case of tertiary alkyl halides here, they mainly undergo E1 reactions, and they can undergo E1 reactions in those weak Lewis bases like water and alcohol, because it can wait for the carbocation. The carbocation is relatively stable. Okay. However, because we don't actually have the steric demand from the backside attack that we had with the substitution reaction, we're actually pulling the hydrogen off one carbon away. They can also undergo E2 reactions in the presence of strong bases like hydroxide and alkoxides. Okay. Now, because so many of the nucleophiles are actually strong bases like hydroxide and alkoxide, SN reactions or substitution, nucleophilic substitution reactions, and beta elimination reactions often compete. Okay, so the ratio between the substitution reaction and the elimination reaction depends on two things. First of all, it depends on the strength of the nucleophile or the strength of the base. Okay. So in the presence of something like a primary alkyl halide, okay, in reactions with secondary and tertiary alkyl halides, a polar protic solvent gives mixtures of substitution and elimination products as well. The product ratios are difficult to predict because, remember, in the secondary and tertiary haloalkanes, we can form that carbocation. Once you form that carbocation, it is the most reactive species. Therefore, it can eliminate through an E1 reaction, giving us a alkene product. It can be substituted by the solvent itself or by one of the other species in there to give other products. Okay, it's considerably easy to predict the product ratio for SN2 and E2 products because we only have a concerted reaction. It's based on the nucleophilicity of the attacking group and the ability of the group to lead. Okay, so in this case, attack of the base on the beta hydrogen by E2 only slightly affected by the branching of the carbons because it's one carbon away from where the leaving group is. So sterics aren't as big a demand. And in the SN2 attack, remember that the nucleophile is impeded by these materials here. So that we use a strong base, we can improve our chances of getting an E2 reaction for those secondary and tertiary alkyl halides. Okay, so now let's summarize this. Just talking about methyl halides and primary halides. Okay, methyl halides will only undergo substitution reactions because there's no way, there's no second carbon for it to remove that proton from. Remember, the alpha is the carbon that alkyl halide's on, the beta is the carbon next to it. Okay, So now with alkyl halides, with an alkyl halide, you can have a carbon next to your carbon with the halide on it, and therefore you can undergo an E2 reaction. And you tend to do it with very strong bases like potassium T-butoxide. The SN2 reactions happen with strong bases and moderately good nucleophiles. But there are no SN1 or E1 reactions because you cannot form a stable carbocation. Okay, secondary alkyl halides can actually undergo all four of these reactions, and it's all based on the strength of the nucleophile, the strength of the base, and the solvent. So it will undergo substitution reactions in the presence of weak bases but good nucleophiles, okay? So because it's a weak base, it's not going to undergo an elimination reaction. And because it's a strong nucleophile, it's going to go an SN2 reaction and not an SN1 reaction. In the presence of very strong bases that are also good nucleophiles like hydroxide and alkoxide, we will get elimination reactions because that base will come in, pull that beta proton off, and give us our leaving group. Now, if we have weak nucleophiles in polar solvents like water, methanol, and ethanol, remember, water, methanol, and ethanol are all weak nucleophiles because they're lone pairs. Those can undergo a combination of SN1, E1 reactions, and we will see both of those products available to us in those systems. Once we get to the tertiary alkyl halide, we of course have no SN1, SN2 reactions because of the sterics. We will undergo easily forming the carbocation, therefore the E1 SN1 reactions will happen, but these happen when we have very poor nucleophiles or very weak bases, meaning we're waiting for the carbocation to form first, and then the weak base can remove the hydrogen on the beta, or the attacked as the nucleophile. Now, in the case of an E2 reaction, because we're one carbon off from the alkyl halide, sterics plays less of a role. Therefore, if we have a very strong base, we will not get substitution reactions. We will tend to get elimination reactions. So an tertiary alkyl halide with a strong base will give us elimination reactions. Tertiary alkyl halide with weak nucleophiles or weak bases or non-charged nucleophiles will give us SN1, E1 combination reactions. Okay, so now to summarize all of these reactions in all of chapter 7, okay? Methyl halides tend to not react with things like water. There's no reaction, there's no SN1, no SN2. If we have a weak base, a good nucleophile, or a strong base, or even a hindered base, something big and bulky like T-butoxide, it will undergo SN2 reactions only. Okay? It cannot form a carbocation, it'll only undergo the substitution reactions. Once we have our primary alkyl halides here, we can then, again, with poor nucleophiles like water, they do not react. We must have at least a good nucleophile or a good base for them to react. In the case of a good nucleophile, the substitution reaction is favored because we have a strong charged nucleophile. Okay. If we have a poor nucleophile or a strong base, we now can get some competition between an SN2 reaction and an E2 reaction. Okay. If it's an unhindered, there's a possibility for that SN2 reaction. However, if that alkyl group starts to branch, it starts to get bigger and bulkier, we are favoring an E2 reaction, where we are doing an elimination process with the absence of a carbocation. And in strong bases, they undergo E2 reactions because the protons can be pulled off from the beta carbon. Once we get to secondaries here, they will slowly react as E1, E2 in poor nucleophilic solvents like water. However, with good nucleophiles, they will undergo SN2. And in basic conditions, they will only undergo E2 reactions. our tertiary alkyl halides will slowly undergo SN1 and E1 reactions in things like water. Again, going through that carbocation intermediate. In the presence of weak bases or good nucleophiles, we will still go through that carbocation intermediate. But in the presence of strong bases and strong hindered bases, because the proton is coming off of the carbon next to the carbon on the alkyl halide, E2 mechanism predominates. And that completes our journey in Chapter 7, Alkyl Halides.